Hello, everyone. So today we are going to talk about multiple integrals. Really just double. We'll get to triple probably next week. So we're going to talk about double integrals with the region being rectangular and then extend to more general regions. So right now I just want to talk about the interpretation of a double integral. So if the single integral, definite integral from a to b of f of x dx with f of x being greater than or equal to 0 for all x in ab, if this integral finds area, then what does the double integral of f of x over r dA calculate? With r being, let's just say, some rectangle, a to b cross c to d. You might also see this is like the x values, this is the y values. You might see this as all xy in R2, that's just the xy plane, such that a is less than or equal to x is less than or equal to b, and c is less than or equal to y, which is less than or equal to d. X lies in between a and b, and y lies in between c and d. So that is R, rectangle. So what does this integral find? You know, if anyone showed up to these sessions, I would wait for an answer, but I guess I'll go ahead and tell you. It's volume. It's volume. If the single integral finds area, the double integral finds volume. You know, if f of xy is greater than or equal to 0 for all xy in a to b cross cd. Okay, so let's consider the special case when our function f of xy is the function 1. So what does the double integral over r of 1 dA find? And again, if anyone was here, I would wait for an answer. But no one is. So this integral finds area of r. Now, why does it find that? Well, think about this. So we have r as the base. So the solid with base r and height 1, remember volume is just really area of the base times the height. So if our height is 1, then the volume coincides with the area. Okay. Now make a claim about the definite integral from a to b of 1 dx. Okay. This might blow your mind, but it's actually volume. In one dimension, volume in one dimension, which is length. I tricked you. Yeah, so a single integral with the function 1 over a to b is just what? It would be b minus a. You know, because you could integrate this, as the antiderivative would be x, evaluated from a to b. Use the fundamental theorem of calculus, you get b minus a, which is length. You know, supposing that b is greater than a. Okay. And you know, we can talk about triple integral right now. So what would this triple integral find? You know, E is some oh, okay, let's make it a a box. to say E is all points x, y, z in where? R3, such that A is less than or equal to x is less than or equal to b, and y lies in between C and D, and z lies in between E and F. So we would have some box, and that's what we're integrating over. Well, really, we experience too few dimensions to have a good geometric interpretation of what this is, unfortunately. So it's some sort of quote unquote, I've heard a book describe it, I read a book describe it as a hypervolume. But you can actually extrapolate some physical interpretations. If I'm not mistaken, if your function f is density, and then imagine this dv, think about, density. What is density? Density is mass over volume. Okay, well, if we multiply by volume on both sides, we have mass is equal to density. Let's say density as a function of x, z times volume. Well, that would just be the mass of an object with variable density over some volume. So a hypervolume, if you will, or you can look at it as this mass. Also, what would be the triple integral over E of 1 dV is equals volume. So when your function is 1, it sort of like bumps it down one dimension. Yeah, so on to the next slide. Volume below the plane. This is out of Stewart's calculus book, 7th edition. I'm sure it's somewhere in the 8th. Page 987, number 23. Sketch the solid whose volume is given by the aerated integral. Okay. So we'll look at this as the function f of x equals 4 minus x minus 2y. And say, well, if f of xy equals this, then that's like the same thing as z equals 4 minus x minus 2y. Which is to say x plus 2y plus z equals 4. This is the level set equation of a plane. Okay, so well, we can actually draw this plane using techniques found in chapter 12, 13 question mark. I think it was 12. Okay, so we're gonna sketch the intercepts and just kind of make like a triangle out of that. So let x equal y equals 0. This would find the intersection with the z-axis. Z equals, well, you get 0 plus 2 times 0 plus z equals 4. That is z equals 4. Okay, so drawing our axes, x, y, z. Okay, z equals 4. Uno, dos, tres, cuatro. 4. Okay, cool. Now, let's see. Let's find x equals z equals 0. That would be when y equals 2. 1, 2. Okay, now let y equals z equals 0. X equals, again, 4. 1, 2, 3, 4. Okay, so then we just connect the dots. Alrighty. Okay, but what is our region in the xy plane? Our region is 0, 1 cross 0, 1 from the limits of integration. So R is 0, 1 cross 0, 1. Or, if you will, all points xy in R2 such that 0 is less than or equal to x is less than 1, 0 less than or equal to y is less than or equal to 1. Okay, well that is just a tiny little box right here. It doesn't quite get to the end of our plane, or it doesn't get to the intersection of the xy plane with our plane. That would have to go out probably 2 in the y direction. But we have this tiny little region, and then you just go up to your surface. Right, we go up, and that'll be little 4. If we're at 0, 0, then it would go all the way up to 4, right? Because of this fact. And so it's like kind of like you could probably find the volume geometrically, or you could use double integrals. You could actually even use a triple integral to do this. I might even show you how to do that. And then this one would go up to about here, come down, and so we get some sort of, I don't know, it's like a rectangle with a triangular prism, a rectangular prism plus a triangular prism. So something like that. Okay. Okay, so now it says evaluate, so we will evaluate. So let's see, we have integrating x first and then y. So if we look at our region in R2, we got 0, 1, 1. Remember, dx, dy is horizontal cross sections. It doesn't make a difference right now because of Fubini's theorem, but when we get to more general regions, it will play a more significant role. Okay, so dx, dy is associated with horizontal cross sections. If you don't know what that means, in Stewart's calculus book, what they call it, I think it's type 2 region. A type 2 region. Or I've also heard it as y simple or x simple. I think type 2 is y simple. I'm not sure. I just call it horizontal cross sections when we have dx, dy. Okay, and it'll come more into play at more general regions. All right, so let's evaluate this integral. Let's integrate x. So we got the integral from 0 to 1. This is the outer one, remember. Like this. And then like this. So we got, the integral 0 to 1. We're going to integrate x. So what do we get? We get 4x minus x squared over 2 minus 2xy. Evaluated from 0 to 1, dy. Okay. Now we can use the fundamental theorem of calculus. What do we get? We have 0, 1. Okay, now we're going to plug in 1, so we get 4 times 4, but then we get minus 1 squared over 2, so that's 4 minus 1 half. 4 is 8 over 2. 4 equals 8 over 2, and then 8 over 2 minus 1 half is 7 over 2. So we're left over with 7 over 2 minus, and then we just get 2y dy. Okay, 8y, we have 7 over 2y minus y squared. It's 2y squared over 2. 2 divided by 2 is 1. Evaluated from 0 to 1. What is this? This is, drumroll, 7 over 2 minus 2 over 2. Which is what? This is 5 over 2. So I'm going to stop for a second and ask if there are any questions. Just kidding, there's no one here. All right. So I think I did that right. That was a pretty straightforward integral. We could have also done dy dx, which would be a vertical cross section, but it doesn't matter in this case. It's rectangular. It's square, in fact. Okay. So our volume below the plane and above the xy plane is 5/2 cubic units. Okay. Now we got the volume of the solid enclosed by the paraboloid. Z equals 2 plus x squared plus y minus 2 squared. Okay. So we're going to do a little bit of drawing first. So we know this from, this is a quadric surface. Remember, this was from chapter 12.6. This is a quadric surface, a paraboloid. It's a paraboloid shifted up 2 units and 2 units in the y direction, and it stays at x equals 0 for the center. Okay, so let's go ahead and okay, well, first this stuff, our bounding planes. Let's just look at it in R2, in the xy plane. Okay, so what do we have? We have -1, +1 in x, and then from y we have 0 to 4. So this is our region. And then what do we have? We have the center. 1, 2, 3. So it'd be like right here, but shifted up 2 units in the XYZ plane or coordinate system. So let's kind of get a picture. So what do we have? We have x-axis I'm drawing right now. We have the y-axis right here, and we have the z-axis. Okay. So I guess first let's draw what our region looks like. The picture from over here moved over here. What do we have? We have -1, +1, 0 to 4. So this is our region. Okay. And then we have, it's shifted up 2 units from this +2 right here. So I'm going to count up 1, 2. I'm going to count over 2. Stay on the y-axis because x has not been shifted at all. So my the tip of the paraboloid is actually right here. Okay. And what do we have above it? A paraboloid. So this is what it looks like. Okay. And then we're not finding from below the paraboloid to the xy plane. We're finding from below the paraboloid to the plane z equals 1. That is right here. We have this plane. And so it's like subtracting off function 1. So really, this is the same problem as, finding the volume below z equals 1 plus x squared plus y minus 2 squared. Finding the volume from below this paraboloid to the xy plane to this paraboloid is the same as finding the volume between z equals 1 and z equals 2 plus x squared plus y minus 2 squared. If you remember from 2414, you could have, I think it was like the first chapter in that class, or like chapter 6. You had, okay, well, if we had like, finding the area between these two, we're finding this area, what do we do? If this is the function y equals g of x, and this is the function right here, and right here is the function y equals f of x, what do? You take the integral. This is the intersection AB. What do? You do the integral from a to b of the top function, which is g, minus the bottom function. That would find the area. It's the same constant, just with volume. So we're doing the top function being our paraboloid, the bottom function being z equals 1, thus 2 plus x squared plus y minus 2 squared minus 1 is 1 plus x squared plus 2, or y minus 2 squared. Okay, so there's another trick we can pull with this integral. It's symmetric about the y-axis. So we can integrate x from 0 to 1 and double it. So that's what we're going to do. We're going to do 2 times the double integral of 1 plus x squared plus y minus 2 squared. And then what do you want to do, dx dy or dy dx? I don't think it really matters. Sometimes, you get some benefit from choosing one over the other. Let's just do dy dx. That is vertical cross sections, like so. Okay. So if it's dy dx, we're integrating from 0 to 4. And then x, we're integrating from 0 to 1, right? Because -1 to 1, symmetric about the y-axis, just double half of the integral. Okay. So what do we get? We get y plus yx squared. And I was getting in trouble with this earlier. So what do we have? We have the integral y minus 2 squared dy from 0 to 4. Okay, well, this is the integral from 0 to 4. I know you can use u sub, but I was messing it up earlier. We have y squared minus 4y plus 4 dy. So integrating this, we have y cubed over 3 minus 2y plus 2y squared plus 4y from 0 to 4. What do we get? This is 64 over 3 minus, that's 4 squared, 16 times 2, 32 plus 16 minus 0. 0 is everything out. We have 64 over 3 minus 16 for just this portion with respect to y. 16 times 3 is 48, so we have 64 minus 48 over 3. So that's going to be, let's see, I'll write it out. 64 over 3 minus 48 over 3. And I wish I had people here to correct me if I make a blunder, but I think this is 16 over 3. So integrate this from 0 to 4. We already integrated this over here, so we can just say, plus 16 over 3 dx. This is proper notation. Now it is. We get 4 plus 4x squared minus 0, so we have 4 plus 16 over 3 plus 4x squared times 2, integrate from 0 to 1 dx. Okay, well, 4 over 1 is the same thing as 12 over 3. And then we have 12 plus 16 is 28, right? So we have 28 over 3. 28 over 3 plus 4x squared dx 0 to 1, 2. Okay. And what do we have? We have 28 over 3x plus 4 over 3x cubed from 0 to 1. And then you double it. Okay. What do we get? Well, okay, so 1 just makes everything the coefficients. And 0 zeroes everything out. So we have 28 over 3 plus 4 over 3 times 2. Is 28 plus 4 is 32 over 3 times 2. So the answer, the volume is 64 over 3. And you can verify that with the book. All right. So that was a pretty complicated problem if you're first starting doing double integrals. It was actually listed as a if you look in the book, the red problems, the problems with the red numbers, which I think that no, this wasn't actually. But the problems in Stewart's calculus book with the red, those are the challenge problems, or so I've heard. Yeah, so the answer, the volume is 64 over 3 cubic units. Tricks and tips is next. Oops. All right. Houdini's theorem. No, I mean Fubini's theorem. If you don't know who Houdini is, he was what did he do? He was like a magician. He did like escape acts where he would be like locked up, thrown into some water, and he would get out of the handcuffs and swim to safety. And I think that's actually how he died, unfortunately. I'm not sure though, but you can look him up. Houdini. I think it's Harry Houdini. Anyways, we're talking about Fubini's theorem. So this is a theorem from the book. If f is continuous on the rectangle, R is the set of all points x, y in R2 such that a is in between, or x is in between a and b, y is in between c and d. I could have just wrote it like, where's my, okay, here we go. A, B cross CD. That's the same thing. Then the double integral over R of f of x, y, dA is, we have the equality between these two integrals. You can change the order of integration so long as you respect, right, the dx, dy, dy, dx. Notice the dy matches up with CD, dx matches up with AB. And then I also have one other nice trick for you right here to the right. So if we have the integral over R of an independent function g of x times an independent function h of y dA, then we can take the product of the two single integrals separately. All right. So this is problem 987, page 987, problem number 19. And this problem was, I'm not going to lie, this was kicking my butt earlier, but we can do it. And I bring this to light, I show you this problem to say that sometimes it's better to choose dy dx over dx dy or vice versa. Sometimes you can cut down computation by choosing to do one over the other. In this case, if you choose to do integrate y first, you have a lot easier time. So let's integrate x first. Oops. All right. Yeah, cool. Hopefully I have enough room. I know I'm not going to have enough room between this problem and the next one. Yeah, but I can skip a page or something. All right, so let's do dx dy first. Notice when we integrate x, what are we going to need? What technique of integration? If anyone was here, I would wait for an answer, but no one's here. So we're going to do integration by parts, right? Because we have an algebraic function times a trigonometric function. Okay, so let's do it. We have the double integral. We're doing x first, so interior is 0 to pi over 6, exterior is 0 to pi over 3 of x sine x plus y dx dy. Okay, and like I said, integration by parts to do x. And so what do we pick for u? And what do we pick for dv? If you don't remember the formula, you should. It's uv minus the integral of v du. Okay, so you pick u based on, I think they call it ilate. Sometimes I see it liate, but ilate works. Inverse trig, logarithms, algebraic, trig, exponential. Order of precedence for picking u. Algebraic comes before trigonometric, so we're going to pick x for u. You calculate du. Du is just dx. dv is what's remaining. What's remaining is sine x plus y. Don't forget your dx. So v would be, okay, well, the integral of sine is negative cosine. You would need a u substitution, technically to do this, but since it's plus a constant, it doesn't really matter. So, I mean, you would pick, let's do t equals x plus y, and then what, dt is dx, so you just replace with t, and then you're good. So it's going to be negative cosine x plus y, no dx, just negative cosine x plus y. Now, let's see. What was I going to say? Oh yeah, check our work. What's the derivative of v? The derivative of v, well, derivative of cosine is negative sine, so we have negative sine x plus y, which is positive sine x plus y. That works. Okay, so we integrated dv correctly. Now we're just going to plug into our formula, uv minus the integral of v du. So we have the integral from 0 to pi over 3 of uv negative x cosine x plus y minus the integral of v du, which is plus the integral cosine x plus y dx. Okay, let's make this proper. Don't skip any steps. We have a dy. This is from 0 to pi over 6. We're integrating this from 0 to pi over 6 in x. Yeah, you get it. The upper and lower limits. Okay, let me go ahead and integrate this cosine x plus y first. So we have 0 to pi over 3. We have negative x cosine x plus y. The integral of cosine is sine. So we have plus sine x plus y. Again, plus integrating by plus a constant. A y is constant with respect to x, so don't need to really worry about the plus y too much. Okay, so that's our antiderivative. We evaluate this from 0 pi over 6, and then we do y, integrate with respect to y. Okay, so what do we get? We have 0 pi over 3 okay, we have negative pi over 6 cosine y plus pi over 6 plus sine y plus pi over 6. Okay, dy. Let's integrate this with respect to y, because why not? No, I'm kidding. That's what we have to do. Okay, so the integral of cosine, you retain the sign, so we have negative pi over 6 sine, negative pi over 6 sine y plus pi over 6. When you integrate sine, you reverse the sign, minus cosine, y plus pi over 6. And we evaluate this from 0 to pi over 3. Okay, so we have, what do we have? We have negative pi over 6. Okay, now look at this. We have sine of, we're going to plug in pi over 3 for y. Okay, well, pi over 3 is really 60 degrees. Pi over 6 is really 30 degrees. So think about it this geometrically. This is really sine of pi over 2, which is 1. And then we have minus cosine of same business, pi over 2. Luckily, that's 0. Okay, now we subtract off. We have negative pi over 6 sine 0 plus pi over 6 is pi over 6. Minus cosine pi over 6. I think I did this right. Wow. Okay, so this is 1. This is 0. This is 1/2. This is root 3 over 2. So we have negative pi over 6. And we flip the sign of everything in here. I'm missing a term, I think. So we get plus pi over 12 plus root 3 over 2. Crap. Because I need, I'll show you the answer actually. The answer is 1/2 square root of 3 minus 1 minus pi over 12. Where did I mess up? Oh, I messed up right here. I forgot to plug in 0 for my lower limit on x. Yeah, so check this out. So plugging in pi over 6, I get, this first one. Then I subtract off, plugging in 0. The first term is 0. The second term is just sine of y. Okay, so we have a minus sine y. Integrating minus sine y just makes it plus cosine y. And then we plug in a pi over 3 and a 0. Pi over 3, cosine of, we get plus cosine pi over 3 minus cosine 1. Cosine pi over 3 is 1/2 minus 1. This is negative 1/2. Yeah, it worked out perfect. Okay, yeah, so we have, what does this combine to? This is negative 1/6 plus 1/12 is negative pi over 12. And factor out a 1/2. We have square root of 3 minus 1 from this guy. Yeah, so perfect. Okay. Now we're going to do the same problem just with dy dx. We're going to see it's easier. So let me do it over here. We have the double integral x sine x dy dx. 0 to pi over 3, 0 to pi over 6. Make sure I got this right. X sine x. Okay, cool. So we just flip the order of integration and flip the bounds. All right. So integrating y first, x is constant here and here. So the integral of sine, what do we get? We get 0 pi over 6. The integral of sine would be, you flip the sign when you integrate sine. So that's negative x cosine x plus y integrated from 0 to pi over 3 dx. Okay, well, if we plug in our bounds. These are y's, right? So we get 0 to pi over 6, negative x cosine x plus pi over 3. And you minus negative makes it plus x cosine x plus 0 is x. Dx. Okay. Oh, wow. We need 2 integration by parts this time. But remember, plus constant inside the cosine, that doesn't really change the derivative all too much. You can just shift the derivative, right? Horizontally, more or less. So anyways, we're going to go through this IBT real quick. So what do we pick? Let's just do this one. So So we have u equals x, du equals dx, dv equals cosine x plus pi over 3, v equals the integral of cosine. You respect the sign, x plus pi over 3. Okay, so we get uv. All of its flip sign too, because we have this negative right here. So uv minus the integral of v du is uv minus the integral of v du. Well, we have a negative right here, so it's plus the integral of v du. Okay. And then, you know, what's this antiderivative going to be? It's going to be the same thing. It's going to be plus x sine x minus the integral sine x dx. Okay, so what do we get? Let's integrate these two first, and then let's plug in our bounds. Our bounds are 0 and pi over 6. So we have negative x sine x plus pi over 3. The integral of sine, you reverse the sign, minus cosine x plus pi over 3 plus x sine x. Integral sine, you reverse the sign, plus cosine x. Integrated or evaluated from 0 to pi over 6. Get negative pi over 6 sine pi over 2 minus cosine pi over 2 plus pi over 6 sine pi over 6 plus cosine pi over 6 minus negative 0 minus cosine pi over 3 plus 0 plus 1. This is sine 0 and this is cosine 0. Okay, so this is 1, this is 0 minus pi over 6 plus pi over 12. This is looking familiar. Plus, what is cosine of this? Plus root 3 over 2. So we get, okay, this is 1/2. This is negative 1/2 plus 1. Positive 1/2, but we're making it negative from this guy. So this is minus 1/2. Perfect. First time. Wow. Okay, minus pi over 12 plus 1/2 square root of 3 minus 1. QED. All right. So that was doing this problem, this animal problem using verifying Fubini's theorem. We got the same integral doing it both ways. Okay. Now we have doing the independent functions of x and y being multiplied. Look at this. This is okay. We got 0 to 1, 0 to 1. So it doesn't matter. We got 0 to 1, 0 to 1, and then this is really 1 plus x squared times 1 over 1 plus y squared dy dx. This is a function of x times a function of y, so we can multiply the single integrals. Okay, well, this is simple. This is x plus x cubed over 3 0 to 1. If anyone was here, I would say, what is the integral of 1 over 1 plus y squared? And then I would wait for an answer, and someone would type it in. No one's here, so I have to tell you. Yeah, so the integral of 1 divided by 1 plus y squared is arctangent, tangent inverse. Arctangent y, evaluated from 0 to 1. Okay, so we get 1 plus 1/3 is 4/3. Then we get times arctangent of 1 is pi over 4. And arctangent of 0 is 0. Multiply, this equals pi over 3. That was a lot easier than trying to do a double integral, I suppose. Okay. So that was tricks and tips. Yeah, we're getting through this quicker than I thought. So actually, at this point, like right here, at this point, I when I was preparing, I lost my stylus for my good writing pad, and I had to revert to my pixelated writing pad. That's why these words look kind of pixelated. But then I found it right before the session, so yeah. But this is what I was talking about: vertical cross sections or horizontal cross sections, double integrals over general regions. Okay. So if you look in your book, actually, in 15.3, let's see. Yeah, so 15.3, it talks about the double integrals. And so, basically what's going to happen with this is we have, two options. We have vertical cross sections, which is dy dx, like that. Horizontal cross sections, like that. Oh, not dy dx, dy dx, and dx dy. Okay, so I'll show you a dy dx region. Okay, that's not dx dy. Okay, let me think about this. So if we're talking about R2, talking about regions in R2, that yeah, we can do this. And say this is like A and this is like B. So in between A and B, here's like literally this is how my teacher taught me, but it works. He's like, all right, guys, so you draw a little dude, you draw your little stick figure, and notice his floor is the same all along here. So that means for every vertical cross section I take, I could do it right here, I could do it right here, or I could do it right here. But anywhere I do it, his floor is always going to be the same, and his roof is always going to be the same. So that's why we do dy dx. We integrate y, then we do x. Okay, now I'll show you a region that we would need horizontal cross sections to do. I'm literally just looking in the book for these because I didn't prepare anything for it, but I thought I could think of some on the spot. But so okay, so we got x, y axes, and then this would be yeah, this is a nice one. Like this. Say this is one function, and this is another function. Okay, so like think if I was trying to do vertical cross sections. Well, I would have, a different floor for right here and a different floor for right here. They're the same roof though. So vertical cross sections wouldn't work. Okay. So if this is, one function and this is a different function, and let's say this is, A to B. Well, then if I draw my dude right here, this is his floor, and then his roof is the same throughout. The floor is the same throughout for any horizontal cross section I can draw. So that's why we would use dx dy in this situation. It's you draw a picture of a guy. If he's walking along and his floor changes at any spot, you know you did the wrong one, because like to do this region with dy dx, the same region, we would need to split it up into two integrals, which is a pain. It's really a pain. And we're actually going to find out later, some regions you just can't avoid having to do two integrals. I'll show you one. It's a parallelogram. If we do this, oh no, that didn't work. Let's do it kind of skew. Maybe a diamond? Yeah, that works, a diamond. Yeah, I think I like that. Okay, so if I do vertical cross sections, my floor would change from here to here. So rule that one out. If I do vertical cross sections, my floor would change from here, or horizontal cross sections, my floor would change from here to here. So no, I don't have a valid way to do it. You know, like we would have to do two integrals this way, or we'd have to do two integrals this way, which is a pain. And so there's something called change of variables. It's like a U substitution, but for multiple variables. And we'll get to that later. I'm going to leave it as a excitement for next time. I'll show you another one, actually. I can think of one right now. If we had this region. Yeah. Yeah, so his floor changes from right here to right here. Then if we do horizontal cross sections, his floor would change from right here to right here. So we don't have any valid way to do it. Okay. So this is a little to think about how would we change this region, transform it to be a nice type 1 or type 2 region. Okay, so let's look at this surface x times y. I think of this function as like an area, a rectangle. X times y, length times width. Okay, so we have with the triangle with vertices 1, 1, 4, 1, 1, 2. That is our region in R2. So let's go ahead and plot that. Just plot it as soon as you get it. We got 1, 1. We got 4, 1. We got 1, 2. Wow, that's a nice triangle. Okay, so we got 1, 1. We got 4, 1. We got 1, 2. And we're integrating up to x, y. Okay. So do we use horizontal cross sections or vertical cross sections? Well, let's check. If I draw my dude right here, his floor doesn't change the whole time if he walks across, and his roof stays the same as well. Or if I draw my dude right here, his floor stays the same the whole time, and his roof actually stays the same too. It doesn't matter which one you do in this case. It's both type 1 and type 2. I'm going to use vertical cross sections, dy dx, like so. Okay, so we have double integral xy dy dx. Let's look at our bounds. So for y, he's going from 1 all the way up to this entire function right here, which is a linear line. It's an affine function. It's linear, but it doesn't pass through the origin. It's affine. It's affine function. Okay, so let's find the equation of this affine function. Okay, so we got y2 minus y1 over x2 minus x1. This is negative 1 over 3. That's the slope. So we got y minus y1 is equal to m times x minus x1. Got y is equal to negative 1/3 x. This is plus 1/3 plus 2 plus 7/3. So we got negative 1/3 x plus 7/3. Then dx, we're going from 1 to 4. Oops, a bit weird. Okay, 1 to 4. Okay, so we got 1 to 4. X y squared evaluated from 1. Yeah, negative 1/3 x plus 7/3. Then do dx. So we got what do we get? We get 1 to 4 x negative 1/3 x plus 7/3 squared minus x dx. Oh boy. Okay. So now I'm going to do some algebra. Okay, so we got the integral from 1 to 4. X times 1/9 x squared minus twice the product. Twice the product is negative 14 over 9x. And then plus 7/3 squared minus x. Okay. Okay, let's go ahead and distribute. Get 1 to 4. 1/9 x cubed minus 14 over 9 x squared plus 49 over 9x minus x. Okay, let's go ahead and integrate. Let's do 1 over 36 x to the 4th minus 14 over 27 x cubed plus 49 over 18 x squared minus x squared over 2, evaluated from 1 to 4. Okay, so we get 4 to the 4th is 256, right? Because that's a 16 squared. Check that. Oop. Okay, yeah, 256 over 36. We got 4, so we get minus 14 times 64 over 27, plus 49 over 18 times 16, minus 16 over 8. Fractions. I'm going to give you a nice answer, though. I'm determined. Okay, what is 256 divided by 36? 256 divided by 2, 128. This is 64 over 9. Minus 14 times 64 is 896 over 27 plus okay, this is 9 over 8, 49 times 8, 392 over 9 minus 8. How did I do this earlier? Maybe there's some, okay. Oh, look, these. 392 plus 64 is 456 over 9 minus, see if I can bring this down by 3. 896 divided by 3. Nope. Minus 8. Well, you know what? This is going to be left as an exercise for the reader. So, exercise for the reader. That's you. You have to do this. Homework for next time. Yeah, so I mean, you get the idea. I mean, right? We have a double integral over some region that's not a rectangle, and we just use the function instead, right? We use a function for our bounds now. Okay. About changing the order of integration. It's kind of like Fubini's theorem, but careful. General regions. So, okay. Let's look at this problem right here. This is a perfect example of a problem you must change the order of integration. Why? Now, if anyone was here, I would wait for an answer. No one's here, so I'm just going to tell you. You have to change the order of integration. Because why? It has you do dx first, right? It has you integrating x first. If you look, if the integral of e to the x squared dx equals, I don't know, it's a non-elementary function. It has no antiderivative, believe it or not. It's true. Yeah, it doesn't. So that's why we have to change the order of integration. If we change the order of integration, we'll be able to solve this problem. Okay, so check it out. This is like x equals 3y, x equals 3. This is like y equals x over 3, basically. I just divided by 3. Okay, so we have y going from 0 to 1, and x going from, well, we have this x over 3 business, and it goes to 3, so it looks like this. Okay, so what do? We have like this region right here. Why is it to the right? Well, because our lower bound, our floor, if you will, is x equals 3y, which is this line. Then our roof is 3, which is right here. And yeah, so it's this region. So what are we going to do? It has us doing horizontal cross sections right now. But notice this is type 1 and type 2 regions, so we can do dy dx. So that's what we're going to do. We're going to do double integral dx squared dy dx. But be careful now when you change the integration, the limits of integration. So look, the floor, if we do horizontal cross sections, is what? Function 0. Our roof now is this line. This line as y equals is really x equals 3, or x over 3. And then x is going from 0 to 3. Okay, now we can integrate. The integral of e to the x squared dy, that's just y e to the x squared. 0 x over 3. Okay, so now we just plug in the top one, subtract off, plugging in the bottom one, 0 to 3, x over 3 e to the x squared minus 0 just zeroes it out. Okay, now why can we do this integral now? Because it's a different function. Look, it's x times e to the x squared. Now we can do u substitution because the power of e is 1 greater than this power right here. So we do u equals x squared, du equals 2x dx, du over 2 equals x dx. So this is 1/6 0 to 9 e to the u du. So this is 1/6 times e to the 9th minus 1. Let's see, how much more do we have? This is the last problem that I brought for today. I think I want to leave it for next time. We kind of flew through everything. So yeah, maybe exercise for, next time. Bring it next time, and prove to me that you understand this changing the orders of integration. Because look, this function that we have, the integrand, we try to integrate x, we just can't do it. It's a non-elementary function. But if we draw the region, and then change from horizontal cross sections to vertical cross sections, then and only then can we integrate this function. So bring it to me next time, or yeah, that's all I got for today. And I'm gonna leave you with my signature. Howdy to the -1. It is howdy inverse. That means goodbye.